Hubble Space Telescope. Everyone knows the name. Almost nobody knows what it actually does. It doesn't look at the universe the way your eyes do. It looks at the universe the way your eyes wish they could. Visible light plus a slice of ultraviolet. The same basic categories of light your retina already processes, just sharper, deeper, and utterly unshaken by the atmosphere sitting on top of you. Here's the number that matters. Hubble orbits 547 kilometers up, circling Earth once every 95 minutes. That's above the atmospheric blur that turns every star you've ever seen into a twinkling smear. No twinkle up there. Just a fixed, merciless point of light recorded exactly as it left its source. It launched in 990. It was supposed to see with perfect clarity. Instead, its primary mirror turned out to be ground wrong by a margin thinner than a human hair, 2.2 microns off, enough to blur every image it produced. NASA had to send astronauts on a repair mission just to give the telescope glasses. Let that sink in. Humanity's premier eye on the universe needed corrective lenses, fitted by hand, 547 kilometers above the ground, by people in pressurized suits holding tools with tethers so they wouldn't drift into the void. Once it worked staggeringly well. In 1995, astronomers pointed Hubble at a patch of sky the size of a grain of sand held at arm's length, a patch that looked completely empty. They left the shutter open for 10 days. What came back wasn't emptiness. It was 3,000 galaxies packed into a sliver of darkness nobody thought was worth looking at. Here's the fact that changes everything. If a patch of nothing, the size of a grain of sand, contains 3,000 galaxies, the entire sky contains something like 2 trillion of them. 2 trillion galaxies, each with billions of stars, and we only noticed because a telescope stared at a boring spot of sky for 10 days out of stubbornness. Hubble has now been operating for over 3 decades. It has taken more than 1.6 million observations. It has helped measure the age of the universe to within a rounding error, 13.8 billion years, and it has photographed light that left its source before Earth even had continents in their current shape. And it does all of this seeing the same kind of light you're using to read this sentence. Which raises an uncomfortable question. If visible light alone reveals 2 trillion galaxies, what does the universe look like in the light we can't see at all? James Webb Space Telescope. The upgrade nobody was emotionally prepared for. Where Hubble sees what your eyes could theoretically see, Webb sees what your eyes are physically incapable of seeing, ever, under any circumstances. Infrared. Heat. The universe glowing in wavelengths your retina doesn't even have the hardware to register. Here's why that matters more than it sounds. Light from the most distant galaxies has been stretched by the expansion of space itself, a phenomenon called redshift. The farther back in time you look, the more that light gets dragged from visible wavelengths into infrared, which means the earliest galaxies in the universe are quite literally invisible to a telescope like Hubble. Not faint, not blurry, invisible. The wrong tool for the wrong kind of light. Webb fixes that by being built almost entirely around the problem of heat, including its own. Its instruments have to run at minus 233 degrees Celsius, colder than almost anywhere else humans have engineered, because even the telescope's own warmth would flood its sensors with false signals. To achieve that, Webb carries a sunshield the size of a tennis court, 5 layers thin as human hair, folded like origami to survive a rocket launch, and then unfurled a million miles from Earth at a gravitationally stable point called L2, where it has stayed in permanent shadow ever since. A million miles, 4 times farther than the moon. Far enough that if something breaks, there is no repair mission. No astronauts with tethers this time. Just months of engineers on the ground holding their breath through 344 separate single points of failure during deployment, any one of which could have ended the $10 billion mission before it saw a single photon. None of them failed. And what came back stopped astronomers cold. Webb found galaxies that appear fully formed just 300 million years after the Big Bang. Galaxies that, according to the standard models, shouldn't have had time to exist yet. Structures too big, too early, too organized. The universe, it turns out, got its act together faster than anyone predicted. And we only know that because we finally built an eye tuned to the specific color of ancient light. Here's the part that should genuinely bother you. Webb isn't just looking further back in time than Hubble. It's looking at a category of information Hubble was structurally blind to, no matter how long you left its shutter open. 2 trillion galaxies were already too many. Now there's an entire additional layer of them, glowing in a color humans didn't evolve to perceive, sitting there the whole time. But heat and light aren't the only currency of the invisible universe. Some of the most violent places out there don't glow gently at all. They scream. Chandra X-ray Observatory. This one doesn't do subtlety. Visible light and infrared come from calm things, stars steadily burning, dust steadily glowing. X-rays come from violence, matter torn apart, gas heated to millions of degrees. Chandra was built to stare directly at the universe's most catastrophic events and not blink. Here's the science that makes it necessary. Earth's atmosphere absorbs X rays almost completely, which is good news for your skin, but bad news for astronomers because it means no ground based telescope, no matter how large or expensive, will ever detect them. X ray astronomy only exists because we put the detector in space above the shield that keeps us alive. Launched in 1999, Chandra orbits in a long looping ellipse that carries it a third of the way to the moon, 139,000 kilometers, at its farthest point, 60 times higher than Hubble. It needs the distance to escape Earth's radiation belts, which would otherwise drown its faint X ray signals in noise. And what it finds when it looks is the debris field of cosmic violence, the hot gas screaming out of supernova remnants at speeds exceeding 10 million kilometers an hour, the superheated disks of matter spiraling into black holes, compressed and accelerated until friction alone heats them to tens of millions of degrees, hot enough to emit X rays before the material crosses the point of no return. Here's the fact that changes everything. In 1999, Chandra captured direct X ray evidence of a supermassive black hole at the center of our own galaxy, flaring as it consumed material. Proof that the thing sitting 26,000 light years from you, the thing your galaxy is quietly orbiting, occasionally has violent tantrums, bright enough to detect from Earth. Sagittarius A isn't dormant, it's just quiet most of the time. Chandra caught it not being quiet. Chandra has also mapped the Bullet Cluster, 2 galaxy clusters that collided at millions of kilometers per hour, and in doing so, gave astronomers the closest thing they have to direct visual proof that dark matter exists. The hot gas, visible in X rays, got dragged and slowed by the collision. The mass, measured separately, through gravity, kept moving straight through, unaffected, as if it were made of something that doesn't interact with normal matter at all. Because it is. Here's the part that should genuinely bother you. Everything Chandra sees is violence you would never survive witnessing up close, and it's happening constantly, silently, all around a universe that looks perfectly calm through a visible light telescope. Peaceful starlight and screaming X rays are coming from the same sky at the same time. You just can't see both at once, unless you build 2 different eyes. Not every eye on the sky is still open, though. One of them already closed. Spitzer Space Telescope, the one that quietly retired. Before Webb, there was Spitzer, an infrared telescope launched in 2003, doing the exact job Webb does now, just smaller, colder, and 30 years earlier than the technology was really ready for. Spitzer proved the concept before anyone dared build something as ambitious as Webb. Here's the trick that made it work. Rather than fighting Earth's heat with a giant sun shield, Spitzer simply left. It was placed in an Earth-trailing orbit around the sun, drifting slowly farther and farther behind our planet, putting distance between itself and the warmth of home. By the time it retired, it was over 260 million kilometers behind Earth, farther than the distance from Earth to the sun itself. Spitzer carried liquid helium coolant to keep its detectors near absolute zero. That coolant was always going to run out, and it did in 2009 after 5.5 years, far outliving its planned mission of 2.5. When the coolant depleted, engineers didn't give up. They kept 2 of its infrared channels running in a warm mission for another decade, squeezing a full extra decade of science out of a telescope that had already technically died. Here's the fact that changes everything. Spitzer detected 7 roughly Earth-sized planets orbiting a single star just 40 light years away, TRAPPIST-1. 3 of them sitting in the star's habitable zone, the range where liquid water could exist. 7 planets, 1 star, discovered by a telescope that couldn't see visible light at all, using nothing but the faint infrared dimming as each planet crossed in front of its star. Spitzer operated for over 16 years before NASA finally switched it off in January 2020, ending the mission not because it broke, but because its orbit had drifted so far behind Earth that pointing its antenna home had become an engineering nightmare. It didn't fail. It just got too far away to keep talking to us. Here's the part that should genuinely bother you. Spitzer is still out there right now, tumbling silently through interplanetary space hundreds of millions of kilometers away, completely dark, completely done, a dead eye that once helped discover an entire solar system of Earth-sized worlds. It will keep drifting for the rest of human history, and no one is ever going to go get it. Some telescopes look outward at everything. Others were built to look at one very specific kind of shadow. Kepler and TESS, the planet hunters. Hubble and Webb and Chandra are generalists. They look at whatever's out there and try to understand it. Kepler and its successor TESS do something narrower and, in some ways, stranger. They stare at stars and wait for them to blink. Here's the method, and it's almost embarrassingly simple. When a planet passes directly in front of its star, from our point of view, a transit, it blocks a tiny fraction of that star's light. Earth passing in front of the sun, seen from a distant star system, would dim the sun's brightness by about 0.008%. Kepler was built to detect dimming that small across more than 150,000 stars simultaneously for years at a time without blinking first. Kepler launched in 2009 and stared at a single patch of sky near the constellation Cygnus for 4 straight years. It found over 2,600 confirmed exoplanets before a mechanical failure. 2 of its 4 reaction wheels broke, crippling its ability to hold steady, forced NASA to repurpose it into a second mission called K2, which found hundreds more before it finally ran out of fuel in 2018. Here's the fact that changes everything. Before Kepler, astronomers had confirmed only a few hundred exoplanets in the entire history of observational astronomy. Kepler alone found thousands, and in doing so, allowed scientists to statistically estimate that our galaxy contains at least 100 billion planets, likely more planets than stars. Every star you can see with the naked eye almost certainly has worlds orbiting it that you will never see at all. TESS took over in 2018, trading Kepler's narrow, deep stare for a wide, shallow survey, scanning nearly the entire sky, star by star, looking for transits around stars close enough that follow-up telescopes like Webb could actually study the planet's atmospheres afterward. TESS has already found more than 7,000 planet candidates, including small rocky worlds within reach of detailed chemical analysis. Here's the part that should genuinely bother you. Every single one of these planets was found not by seeing it, but by watching a star get very slightly, briefly dimmer and doing the math. We have never taken a real photograph of most of these worlds. We know entire planets exist purely because a distant sun blinked, and a machine was patient enough to notice. Space-based telescopes are extraordinary, but they're not the only way to build an eye. Some of the most powerful instruments on Earth never leave the ground at all. They just work together. Radio telescope arrays, ALMA and the VLA, the eyes that don't need to launch. Radio waves are the longest, lowest energy form of light there is, and unlike X-rays or most infrared, they pass straight through Earth's atmosphere. Which means, unlike almost everything else in this list, you don't need a billion-dollar rocket to see them. You just need a very large antenna, or better, hundreds of them working as one. The Very Large Array in New Mexico uses 27 individual radio dishes, each 25 meters across, arranged in a Y-shaped pattern that can be physically reconfigured, moved along rail tracks to change the effective size of the array from 1 kilometer to 36 kilometers wide. The Atacama Large Millimeter Array in Chile does something even more extreme: 66 high precision antennas, sited at 5,000 meters altitude in one of the driest places on Earth, where thin, dry air lets millimeter wavelength radio light through almost undisturbed. Here's the trick that makes this work, and it's one of the strangest ideas in observational science. Combine the signals from dozens of separate dishes using the exact timing differences between when each one receives a wavefront, and you can synthesize a telescope with the resolving power of a single dish as wide as the entire array. It's called interferometry. Effectively, you're building a mirror the size of a mountain range out of instruments that never touch. Here's the fact that changes everything. In 2019, the Event Horizon Telescope, a global network including ALMA, effectively an interferometer the size of planet Earth, produced the first ever direct image of a black hole's event horizon in the galaxy Meidi 755 million light years away. That image, a blurry orange ring around absolute darkness, required linking radio dishes on multiple continents, synchronized with atomic clocks accurate to a fraction of a second, to achieve resolving power sharp enough to photograph an object smaller than our solar system at a distance so vast the light took 55 million years to arrive. Radio arrays have also mapped the structure of star-forming clouds invisible in every other wavelength, tracked the faint afterglow of the Big Bang itself in the cosmic microwave background, and detected fast radio bursts, millisecond flashes of radio energy so powerful they release more energy in a thousandth of a second than the sun does in days, and whose exact origin is still genuinely not fully settled science. Here's the part that should genuinely bother you. We built a telescope the size of Earth by never launching anything at all, and used it to photograph an object so extreme it swallows light itself. And still, some of what these arrays detect, brief, violent, unexplained bursts from unknown sources billions of light years away, remains a mystery nobody has fully solved. Not for lack of trying, for lack of enough data from a universe that doesn't repeat its experiments for our convenience. But light, visible, infrared, X-ray, radio, all of it is still only one category of signal. Some of the most extreme events in the universe don't emit light at all. They shake space itself. Gravitational-Wave Observatories, LIGO and Virgo. Not telescopes. Something stranger. Every instrument up to this point has been detecting electromagnetic radiation, some flavor of light. LIGO and Virgo detect something categorically different: ripples in the fabric of spacetime itself caused by the most violent accelerations of mass the universe produces. Here's the concept, and it sounds almost too strange to be real. When two black holes spiral into each other and merge, they don't just release energy as light, often they release almost none. Instead, they physically stretch and squeeze space itself, sending a ripple outward at the speed of light that briefly, imperceptibly, changes the actual distance between objects as it passes through them, including you, right now. Extremely faint gravitational waves are almost certainly passing through your body as you read this sentence. LIGO detects this using two L-shaped facilities, one in Louisiana, one in Washington state, each with arms 4 kilometers long. A laser is split and sent down both arms, bounced off mirrors, and recombined. If a gravitational wave passes through, it stretches one arm and compresses the other by an almost incomprehensibly small amount, roughly 1/10,000th the width of a proton. To detect a distance change smaller than the nucleus of an atom across a 4-kilometer arm is one of the most precise measurements ever attempted by human beings. Here's the fact that changes everything. On September 14th, 2015, LIGO detected its first gravitational wave, the signal from two black holes, 29 and 36 times the mass of the Sun, merging 1.3 billion light years away into a single black hole and releasing more energy in a fraction of a second than every star in the observable universe combined emits in light, all at once, as pure spacetime distortion. No telescope on Earth saw a single photon of it. We only know it happened because space itself briefly, physically rang like a bell, and we happened to be listening. Since then, LIGO and Virgo together have detected roughly 100 confirmed events. Black holes merging with black holes, neutron stars merging with neutron stars, and in 2017, an event detected by both gravitational waves and traditional telescopes simultaneously, proving for the first time that heavy elements like gold and platinum are forged in the collision of neutron stars. Some of the gold in the room you're sitting in right now may have been created by an event violent enough to shake the shape of space across a billion light years. Here's the part that should genuinely bother you. Every telescope in this video, no matter how advanced, detects light. LIGO detects the absence of light doing the work. Cataclysms so extreme they warp the medium light travels through, silent to every eye, audible only to an instrument built to feel the universe shudder. And the eyes we have now, staggering as they are already being replaced by ones we haven't finished building yet. The next generation, Nancy Grace Roman and beyond, the eyes still being built. Every telescope covered so far already exists, already works, already has results. The Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer, is scheduled to launch in 2027, and it's designed to solve a problem none of its predecessors were built for: scale. Here's the limitation Roman is meant to fix. Webb and Hubble both have narrow, deep fields of view, extraordinary detail, tiny patches of sky. Roman will carry a mirror the same size as Hubble's, 2.4 meters, but paired with a camera giving it a field of view roughly 100 times larger. It will be able to survey enormous swaths of sky at Hubble level sharpness, fast enough to map billions of galaxies and monitor the wobble and dimming of exoplanets across huge stretches of space simultaneously, instead of one tiny patch at a time. Here's the fact that changes everything. Roman's primary mission includes directly measuring the effects of dark energy, the mysterious force accelerating the expansion of the universe, first confirmed in 1998, still fundamentally unexplained almost 3 decades later. We have named it, we have measured its effects. We still do not know what it is. Roman is being built specifically to narrow that ignorance down by watching how billions of galaxies drift apart over cosmic time. In a single coordinated survey, no earlier telescope had the field of view to attempt. Beyond Roman, the plans get stranger. The Habitable Worlds Observatory, still in early design, is meant to directly image Earth-like planets around other stars and analyze their atmospheres for signs of life. Not inferred from a dimming star, but photographed, however faintly, as its own point of light. Ground-based projects like the extremely large telescope under construction in Chile will use a primary mirror 39 meters across, composed of 798 individual hexagonal segments, to gather more light than every current generation ground telescope on Earth combined. Here's the part that should genuinely bother you, and it's not really about the machines. It's about the timeline. Every telescope in this video was once a proposal on paper, decades before it saw its first photon. Hubble was conceived in the 1940s and didn't launch until 1990. Webb was proposed in 1996 and didn't launch until 2021. The instruments that will define astronomy in the 2040s are being designed right now by people who may not live to see everything those telescopes eventually discover. Which brings us to the uncomfortable summary of everything you just heard. The electromagnetic spectrum we're still blind to. This is the part that should really sit with you. Visible light, the only part of this entire spectrum your eyes can perceive unaided, is a sliver, a rounding error. If you stretch the full electromagnetic spectrum from the longest radio waves to the highest energy gamma rays across the length of a football field, the portion your naked eyes can see would be smaller than a single blade of grass. Here's the inventory. Radio waves, caught by ALMA and the VLA, on the ground, no rocket required. Infrared, caught by Webb, and until 2020, Spitzer, both fighting the enemy of their own heat to see it clearly. Visible and ultraviolet, caught by Hubble, the one category your own biology already partially handles. X-rays, caught by Chandra, screaming out of black holes and dead stars, completely absorbed by the atmosphere that keeps you alive. And beyond X rays, gamma rays, the most energetic light in the universe, produced by the most extreme events known, detected by specialized observatories not covered here at all, because the list of every type of space telescope, done properly, never actually ends. And underneath all of it, LIGO and Virgo listening for something that isn't light at all, spacetime itself, ringing. Here's the fact that changes everything, the one meant to close this out. Every single telescope in this video, combined, every mirror, every dish, every laser interferometer arm, has still only sampled a fraction of what's actually out there. Dark matter, roughly 27% of everything in the universe, emits no light in any wavelength we've ever built an instrument to detect. It has never once been directly seen. Its presence is inferred purely from gravity, from things bending and moving in ways they shouldn't unless something invisible is holding them. Let that sink in. After Hubble's 2 trillion galaxies, after Webb's ancient infrared light, after Chandra's screaming X-rays, after LIGO's rippling spacetime, the majority of the universe is still, right now, completely unseen. Not because we haven't looked hard enough, because we haven't finished building the eyes required to look at all. We are a species of stick figures on a small, wet rock, and in less than a century, we've built machines that photograph light older than our planet, weigh objects we cannot see, and feel the universe shudder from a billion light years away. Not bad for stick figures on a rock.